You ever stop and think about the unsung heroes of our digital world? Nope, it's not the flashy apps or the cool websites. It's databases. These are the powerful, super organized systems working tirelessly behind the scenes of, well, almost everything you do online. So today, we're going to pull back the curtain and see what really makes these things tick.
I mean, really think about that for a second. You've got thousands of agents, millions of people on websites, all trying to book seats at the exact same time. So how on earth does it all stay perfectly in sync? How is it that the moment you buy your seat, it's instantly gone for everyone else? Well, you guessed it. The magic answer is a really well-designed database.
All right, so to really get how this all works, we're going to go on a little journey. First, we'll dive into a world of pure data chaos. Then we'll meet the super librarian that came to the rescue. We'll look at the blueprints and even learn the language they use. And finally, we'll see just how these incredible systems pretty much run our entire world.
So let's hop in a time machine and rewind a bit. Before we had these modern databases, we were stuck in the era of simple file systems. Just try to imagine running that airline we talked about using nothing but a giant, messy collection of text files and spreadsheets. It would be absolute, total chaos.
And this slide really lays it all out, the two different worlds. Over on the left, with file systems, you've got that chaos. Customer info is copied and pasted all over the place. That's what we call high redundancy. And if you update a name in one file but forget another, bam, your data is now inconsistent. And two agents trying to sell the same seat at the same time? A complete concurrency nightmare. Now look at the right. A database system is engineered from the ground up to fix every single one of those problems.
So, how do you solve all that chaos? It's simple, really. You hire a super librarian. And in the world of data, that librarian has a name, the Database Management System, or, as we all call it, the DBMS.
Okay, so a DBMS is the software that does all the heavy lifting. It's not the data itself, it's the program that manages the data. Think of it as the ultimate gatekeeper, the organizer, and the tough-as-nails enforcer of all the rules. It makes sure every piece of information is stored safely and that we can get to it in a snap.
You know, when you get down to it, a DBMS kind of does it all. It gives you the tools to build the database, to ask it questions, and it can handle massive amounts of information. And this is critical, it protects the data. If the whole system crashes, it knows how to recover. If 1,000 people all log on at once, it just handles the traffic. No sweat. It is the perfect solution to all those file system headaches we were just talking about.
So how do we actually build one of these amazing systems? Well, you wouldn't build a house without a blueprint, right? A database is exactly the same. It all has to start with a really solid design plan.
And that blueprint, that's what we call a data model. The most common one you'll see is the entity relationship model, or just an ER diagram. It's basically a visual way to map out all the things, or entities, you need to keep track of. You know, things like customers, flights, and seats, and crucially, how they all connect to each other.
The whole design process follows this really logical path. First, you figure out what you actually need the database to do. That's requirement analysis. Then, you sketch out that blueprint, the big picture plan. That's the logical design, where you make your ER diagram. And finally, you roll up your sleeves and actually build the thing, defining the tables and columns inside the DBMS. That's the physical design.
Okay, so once your database is built, you need a way to talk to it, right? And that language is SQL, which stands for Structured Query Language. It is the universal standard for chatting with pretty much every relational database out there.
And SQL commands, they fit into just a few simple categories. Think of DDL as your construction kit. It lets you define the structure with commands like create table. DQL is for asking questions. That's your select statement. And DML lets you actually mess with the data itself. Insert new stuff, update old stuff, and delete things. It's like a simple toolkit of verbs for anything you'd ever want to do.
And just look at how readable this is. The command is almost plain English. It's literally saying, select the first name and the last name from the employees table where their department is sales. It's such a simple but incredibly powerful way to ask super specific questions and get exactly the answers you need.
Now, a good database isn't just some random collection of tables thrown together. Oh no, there's a real science to organizing it the right way to keep it fast, efficient, and error-free. And that whole process is called normalization.
Honestly, you can just think of normalization as the Marie Kondo method for your data. Its one and only goal is to reduce data duplication. You take big, messy tables and you break them down into smaller, more logical ones. By doing that, you get rid of all that repetition, and you end up with a database that's way healthier and so much easier to work with.
Just take a look at this messy table here. We have to repeat the student's name Alice for every single course she's taking, and the course name Computer Science gets repeated for every student in that class. This is just a recipe for disaster. What happens if someone misspells computer science on just one of those lines? Well, now your data is inconsistent and unreliable.
And here's that same information after we've normalized it. See how clean that is? It's all split into logical pieces. There's one table just for students, another for courses, and a third that just links them together. No more repetition. So now, if Alice changes her name, you only have to update it in one single spot. That, my friends, is the power of good organization.
So all of this stuff, the design, the language, the organization, it all comes together to let databases make some unbelievably important guarantees. These are the unbreakable promises that allow us to trust them with our most critical information, from our money in the bank to our airline tickets.
These are famously known as the ACID properties, 4 unbreakable promises. Atomicity means a transaction is all or nothing. Your flight gets booked, and the seat is marked sold, never just one or the other. Consistency makes sure the rules are always followed. You can't book a seat on a flight that doesn't exist. Isolation means my ticket purchase doesn't mess with your ticket purchase even if we both click buy at the exact same millisecond. And durability guarantees that once your booking is confirmed, it is permanent even if the power goes out a second later.
So when you think about it, from the bank that holds your savings, to the airline that flies you across the world, to the online store you just bought something from, databases are the invisible backbone holding it all together. They bring order to what would otherwise be total data chaos, and they allow our complex, interconnected world to just work. They really are the record keepers of our civilization, quietly structuring nearly every digital thing we do. They solved the massive data problems of the present. So the real question is, as our data continues to explode in size and complexity, how will databases evolve to structure our future?